So guys, welcome back. We're going to be continuing our discussion about BGP. In this particular case though, what we're going to be doing is we're going to be taking a look at some of the BGP attributes, the BGP path selection process. We'll get into this in more detail over the next couple of lessons because we are going to have some demonstrations about the BGP path selection process after we discuss our confederation exercise, and then we get into our next hop processing component. Best path selection is essentially kind of what we're talking about now, but it never hurts to see it a couple of different times because it can be really, really complicated, and there's a lot to discuss with regard to how BGP selects different paths. All right, now, as we know from our discussion in our previous lessons, BGP attributes are pieces of information, if you will, that the BGP router attaches to describe different prefixes in our topology. All right, and these BGP attributes allow us to essentially identify how BGP is supposed to treat that particular prefix. We talked about this many, many times. BGP is an application layer protocol, and the purpose of BGP is to advertise what we call network layer reachability information. And we use the underlying IGP to be able to route traffic for those different attributes. All right, now there is a variable sequence, if you will, of BGP attributes in every update message except for BGP withdrawal messages, right, where I'm actually saying the prefix no longer exists and we're going to withdraw the route. Each attribute is a type length value field carried inside of TLVs, and that consists of the attribute type, and then we have the attribute value, or length, excuse me, attribute length, and then finally the attribute value itself. So I talked about this a little bit when we were discussing EIGRP. EIGRP uses a similar construct when disseminating information through the EIGRP routing process. We use these generic containers, if you will, to be able to process information through the protocol. So you can think of these attributes, this TLV attributes, as these containers that contain information. All right, every attribute is 2 octets. Okay, so every attribute is 2 octets, so 2 bytes in size, and one of those is 1 byte is for flags, and 1 byte is for basically the attribute itself, which we're going to discuss in detail in this section here. Attribute details, all right? And we'll see this when we do our demonstrations and we actually get into our configurations and go through that process. We'll see this in Wireshark captures, but it's really important to understand the foundation of these attributes. We've mentioned them a couple of times, right? The last exercise, I talked about local preference, and how we can manipulate local preference to make certain things happen. So it's pretty important to understand these attributes. There are actually different distinctive types that define how routes are going to be used, how we propagate the certain attributes to our neighbors, and so on. These different attribute types are very important to understand, all right? Generally speaking, we have what we call well-known BGP attribute types, and we have optional BGP attribute types. So there's 2 major categories of attributes, and then within those categories we have something called well-known mandatory attributes. And let me just describe these here. So a well-known mandatory attribute is an attribute that must be understood by all BGP speakers. All right, must be understood by all BGP speakers. They don't necessarily have to be used. All right, they don't have to be used. Let me move this down. Here we go. Let's go right here. They don't have to be used, but they need to be understood. What I mean to say by that is that not every attribute is mandatory. Certainly there are some attributes that have default values. Those default values are going to be used. But they don't have to exist in all the updates that I'm necessarily sending to my peers or my neighbors. Under the optional, well, actually I'm not done yet, right? Because we still have another definition here. They're called well-known. And I think I messed up here. I described this one, but this is for this guy here. I'll put that there. We'll get there. All right, well-known discretionary attribute. That's what I meant to say. Okay, I'll just put well-known discretionary. So obviously in this case it makes sense. They don't have to be used. That's the discretionary component of a well-known discretionary attribute. They still have to be understood by all of the speakers, right? But they don't necessarily have to be used. Conversely, with well-known mandatory, the mandatory component of this is that the attribute has to be used, right? It has to be understood by all BGP implementers, and it must exist in the BGP update. So an example, we'll go through how each of these are classified, but as an example, the AS path attribute is what we consider to be a well-known mandatory attribute. Everybody needs to understand it. Everybody needs to include that information in its update because it's one of the key components or key elements to deciding what path I'm going to use for a particular prefix. All right. Now, the other option are the optional attributes, and we have what's called optional transitive, and we have optional non-transitive. Okay? So an optional transitive attribute, as the name kind of implies, means that it does not need to be understood by all speakers. So there may be some attributes that I'm running in my iOS or I'm running in my implementation of BGP that uses or utilizes an attribute that other BGP speakers may not be aware of or may not listen to or may not understand. That's the optional component to that. They can or they cannot utilize that attribute or understand that attribute. The term transitive, all right, there's a flag called the transitive flag. Remember, the first byte in the attribute is set for flags, which means if that transitive flag is set, the attribute is passed to other peers. Well, we'll just call it speakers. All right, so even though I may not necessarily understand the attribute, I don't know what to do with that information, I can still pass that information along to other speakers in case they may want to use that information. All right, so optional non-transitive would be the opposite, right? The transitive flag is not set, which means that I do not need to pass that information to my neighbors. Multi-exit discriminator is an example of a non-transitive optional attribute. I can choose to ignore, actually, I believe it's, yeah, it's optional non-transitive. meaning that my implementation of BGP may or may not understand multi-exit discriminator, and it's a value that once I learn that information from my peer, I do not need to pass that information onto other speakers. In fact, most of the cases, it's not going to be passed on to the other speakers. All right, let me make this a little bit smaller so I can kind of fit everything in the screen here. So those are the general classifications of our BGP attributes. And we're going to go through the process of discussing each of these attributes in detail. And then, of course, we're going to spend quite a bit of time even configuring and manipulating these values. So we've got a type code. We've got the attribute name. And we've got the attribute type. And this will kind of give you an idea of how the attribute is utilized. You know, do I pass it on to peers, speakers? Do I not? And so on. So origin, it would be an example of a well-known mandatory attribute. I'm just going to put WKM, all right, for well-known mandatory. Let's do it this way. So we may not remember that later. Well-known mandatory. WKM. There we go. All right, because we've got quite a few of these attributes to go through. Code 2, that's the most common one, AS path. That's a well-known mandatory attribute. Code 3 is what we call next hop. That's also a well-known mandatory attribute. 4 is what we call a multi-exit discriminator. It's typically written like this, exit discriminator, or what we typically refer to as the MED. That's an optional non-transitive attribute. Optional non-transitive. Now keep in mind what that means. That means that the speakers that I'm communicating with don't necessarily need to know what this attribute is. And even if they do understand it, they don't pass that information along to the other speakers. This is an example of an attribute that eBGP peers use to influence how traffic ingresses or comes into an autonomous system when I have a multi-homed connection to an external AS. We'll get into the details of these as we go through the process here. All right, so we've got local preference. That's type code 5. That's a well-known discretionary attribute. It also happens to be a proprietary one. Discretionary, well-known discretionary attribute. Okay. Discretionary, yeah, make sure I spelled that right. Attribute number 6 is what we call the atomic aggregate, probably one of the most misunderstood attributes that we'll spend some time talking about. We actually have a whole lesson dedicated to that concept. Atomic aggregate is a well-known discretionary attribute. Number 7. What is number 7? Aggregator. That is also an optional attribute. We'll call that an optional transitive attribute. Good old OT. And then we've got, now I'm getting to the list where, I can't remember, but community, I believe, is the next one. That's also optional transitive. And then we've got, there's only 1,000 of these, by the way. Originator ID, I believe, is next. And that's an optional non-transitive attribute. And then we have DPA. Cluster list. We don't usually get to these attributes in our path selection process. We've already made a decision at this point. But we'll still talk about the process and what each of these attributes represent. Now, DPA is what stands for a designation point attribute. And it has to do with the tiebreakers that we talked about. And we'll get more into this when we get into our actual configuration in our labs. But now we're getting into basically all of the tiebreaker scenarios where I've gone through and I've pretty much not able to make a decision based on some of these well-known and mandatory attributes. Let's see, advertiser. I'm not too familiar with this one because we don't get to this point this much. IDRP route server. And I probably don't even need to list these because we're never going to see these. Path, cluster ID. Nope, ID, there we go. This is the same as this one. And 14, we're almost there, guys. This one is kind of interesting, and we'll actually see this in one of our other lessons, what we call multi-protocol reachability and LRI information, and multi-protocol unreachability. So I'm just going to do multi-protocol reach and LRI. Of course, that means I need more space here. Remember, we talked about BGP being a very complicated application when it comes to the decision tree that we go through in our process, right? And you can already see this as part of the discussion. All right, then we have unreachability. And that's also an optional non-transitive attribute. And then finally, the last would be extended communities. And this one's actually not classified as an attribute type. We do have 256, that's kind of reserved. But essentially these, this whole list here is used by BGP routers along the path as I'm advertising or sending out my network layer reachability information to give us the ability to compare different network paths and then essentially select the one that we're going to end up moving into our BGP table and then conversely into our routing table. All right. Now, one of the attributes I actually did not include is the weight attribute. And that's because the weight attribute is Cisco proprietary. It's a local attribute. It's not propagated to in the BGP update message, but it is used by BGP in the path selection process specifically for Cisco. So this would be an optional non-transitive attribute because it would not be something that somebody would have to know, but it's not part of the original RFC. All right. So what we're going to do is we're going to talk about the BGP path selection process and kind of break down what the default values are, and I'll put everything in the notes here so that you guys can reference this if you need to. There's no way you're going to remember this because it's just so much information to go through. But remember, I did show you guys that there was a, cancel that. There was a document on Cisco's website that talks about this process as well. All right. Oftentimes with BGP, you know, we're going to have multiple ways of reaching a particular destination. So the best path algorithm needs to be able to figure out which path I'm going to use. Equal cost multipath routing is not really something that's native to BGP. BGP wants to be able to select a single path for the routing process. All right. So essentially, if I'm learning about prefix X, right, and I'm learning about that prefix from multiple peers, we're still going to do the same thing that we always do with any typical routing process. Longest match routing is going to apply. So if I if I get a 10.10.0.0/16 prefix and a 10.10.10/24 prefix, obviously, or excuse me, a 10.10.0.0/24 prefix, those are still going to be treated as separate paths. Okay. If we assume that all the paths that the router gets for a particular prefix do get arranged in this list, it's essentially the list that we see in the show IP BGP output, right? Some of the paths are not considered as candidates as a path, and that just depends on the path selection process. All right, and we don't need to get into the specifics here because again, I just want to kind of go through the overall process, the decision tree, if you will, the algorithm, if you will, that BGP uses, which we call the best path algorithm. All right, so BGP assigns the first valid path as the best path. And then what happens is BGP starts doing its comparison. It compares that particular path it just selected with the next path in the list until I've reached the end of that entire list. And based on the attributes, that's when I'm going to decide how I'm going to make a decision. All right, so buckle in, guys. Here we go. Number one, we're going to prefer what we call highest weight. All right. Remember, this is a Cisco proprietary decision. Well, we'll just call it a Cisco proprietary attribute. And so it's local to the router on which it's configured, so it is an optional non-transitive attribute. Now, how is weight calculated? Weight is, let me go into Paint here. So let's say, for example, I have a topology here. And I've got some router up here, and we'll just call this AS40. And I've got a router here in AS20. And there's some connection between those prefixes. Some network over here. I've got a router down here. And we'll put this in AS30. Okay. We'll just call that router C. This will be router B. This will be router, and let's call this D. All right. And I've got a router over here. And this is in AS10. Okay. Connected to this router, connected to this router, connected to this router. All right. So let's say that router A is advertising a weight. We need a prefix that we're going to route to. Let's go up here and we'll just call this 10.0.0.0/16. So that's a prefix in that autonomous system. Let me try that again. That's a prefix in that autonomous system that we're advertising to the rest of the domain. I'll use this. So 10.0.0.0/24. All right. So let's say I'm trying to influence my path selection. There we go. I'm trying to influence my path selection, and I'm advertising that prefix from router A. I'm trying to advertise that prefix from router A down to router C, and I'm advertising the prefix from router B down to router C. All right. Let me assign a weight of 100 for the traffic coming in from that router, and let me assign a weight of 200 for the traffic coming in from that router. Now, this is a Cisco-defined attribute, and we use this attribute to select the best path. It is assigned locally by the router. All right, so let me make sure I'm putting in my notes here. Cisco defined attribute. assigned locally by the router. Now what that means from the perspective of our topology diagram here is that the weight is not an attribute that's being propagated by router A and router B. It's an attribute that we're applying to the prefixes as we learn them on router C. So we might have a route map configured on router C that says all the prefixes that I'm learning from B, all the prefixes I'm learning from A, let's go ahead and assign these weight values to those prefixes. All right? But this attribute only makes sense to that specific router. So router C has a decision as a border router, as a eBGP peer to router A and B. It says, am I going to choose to take the path through A, or am I going to choose to take the path through B? Remember, this is the very first attribute in the list that we're going to look at. So AS path is even coming into play here, even though AS path is pretty much the same. We've got two autonomous systems, 10 and 40 going to the left, and two autonomous systems, 20 and 40 going to the right. So the value is not propagated. It's not carried through any updates. That's why we didn't identify a type code for this particular attribute. And it can be a number from 0 to 65,535. So not propagated to any peers, and can be a value of 0 to 65,535, which makes sense, right? Remember the type length value? We had 2 bytes that we use for our attributes. The first byte is for 16 flags, 16-bit flags, and then the second byte is for the attribute itself, which, you know, as a 16-bit field can go from 0 to 65,535 because we use a to the power of 16. All right? Now, paths that the router originates. So if I'm originating a path, it's going to have a default weight of 32,768. All right? But this is only for paths that I originate. Meaning basically the next hop of 0.0.0.0. Okay? It's going to have a default weight of 0 for all other prefixes. All right, default weight of 0 meaning I'm not really assigning a weight to the prefix. Now this is the key. Higher is better. All right. So routers with a higher weight, they have a preference if I have multiple routes to the same destination. So router A has learned about the 10 network from router from AS. Let me go back to the diagram. Router C, excuse me, router A has learned about the 10 network from AS40 from router D. It propagates that update down to router C. Router B also learned about the 10 network from AS40, and it propagates that route back down to router C. So we have 2 ways to reach this particular destination. We have to choose which way we're going to go. If we set the weight of the updates on router C that come in from A, so that weight is greater, in this case double, 200, normally it would be 0, because these are routes that we're learning from that are not originated. Then we simply choose that destination. There's a couple of ways that we can do this. We can do this by using the neighbor command. So here's an example of how to set this. I could say, for example, neighbor, and then specify the neighbor IP. -IP or peer group if we need to specify a peer group. And then I specify, use the command weight, and then I actually specify the weight value. All right. So this can be applied directly to a neighbor relationship. We'll look at other ways that we can manipulate this as well. We can use an AS path access list. So if traffic is coming over a certain AS path, I can use route maps, right? We can use route maps also to set the attribute. And we're going to look at examples of this in every single case, all right? We'll play around with a lot of these different attributes because that may be something that you're going to end up having to do on the exam. You're going to have to go in and set or do some sort of path manipulation with a specific technique to ensure that the traffic takes a certain path. Okay. So I'm not going to get into the details of setting up a route map. Basically, we would create some sort of match condition. We can use an AS path access list, like I said. We can do like apply a route map to the neighbor. That would be like neighbor, neighbor IP, and then say route map name, and in, right? And then in that case, the route map matches an AS path, or it matches a prefix, or matches a prefix list, whatever it might be, and then we just use the set weight command. All right, so there's lots of options. Okay, we can also modify weight to prefer like an MPLS VPN path with IGP as the backup if we want, and so on. So it's a pretty straightforward attribute. It's locally significant to the router itself, and not a whole lot we need to do after that. One of the easiest attributes to manipulate, actually. The next one is the highest. We prefer the highest local preference. Now this, as you see our list up here, local preference is a well-known discretionary attribute with a type code of 5. Remember, type length value is how we carry this information. All right. If I do have a path that doesn't have local preference being considered, it is going to be a default value of 100. But let's go ahead and kind of break down local preference. So I need to draw a different diagram in this case because the way the attribute works is slightly different. So let's say I've got, this one's going to be a little bit more involved. I've got a router here. I'll just throw a couple of different routers in here just to make it look pretty. And I've got a router here. This is router, we'll just call this router C. We'll call this router D. And these guys are in AS, we'll just call it AS51. All right. And these guys are connected on some multi-access network, whatever. They're running some IGP, etc. And they've got a couple of different ASs that they're connected to. Here's router A, here's router B, and I've got, we'll just call this AS10, and we'll call this AS20. And these guys are connected to some prefix up here, and they're connected to our autonomous system. Whoops, sorry about that. Connected to our autonomous system in Area 51. All right. So in this case, we're not using the same, we'll go ahead and reference the same prefix here, 10.10.10.0/24. In this particular case, it's different in weight, right? Because weight, we had one egress router from the autonomous system, and we were making a local decision on how to leave the autonomous system based on the weight that was set on that individual router. In this particular case, though, we have two different routers to leave the autonomous system. We've got router D on the right, we've got router C on the left. So we need to maybe propagate some information, or at least identify a way to leave the autonomous system based on that information. So we would actually set the local preference on router C and router D respectively. So let's say I set a local preference of 150 on that router, and I set a local preference value of 200 on this router. All right, this is a well-known, if you look at the list here, this is a well-known discretionary attribute, which means that all BGP speakers understand what this attribute is, but they can choose to make a routing decision based on it, or they can choose to ignore it. And that's a way we can program the routers to be able to identify this. Okay? So this is a well-known discretionary attribute. It does propagate to its peers. It's an indication, essentially, if you will, to the autonomous system. So it does propagate through the AS, all right? And it's an indication in that AS as to which path has the preference to exit the autonomous system to reach that particular destination, in this case, the 10.10.10.0/24 prefix. Higher is better. I'm going to try and make this consistent in this particular case. Okay? Higher is better. And as far as the values go, the default preference value is 100. In this case, it's always 100. All right? But unlike the weight attribute, which is only relevant to the local router, local preference is an attribute that the routers exchange within the autonomous system. That's what I mean when I say it propagates through the autonomous system. We can set the local preference by using the BGP default local preference command. So I can actually come in here and I can say set with BGP default local preference. And then we would set the value, whatever that value is going to be. All right. There's other ways to manipulate it. Of course, you could manipulate it with route maps as well. And then you're going to see that for the most part, any kind of an attribute that I'm going to be modifying is going to be an attribute that can be manipulated through the use of route maps based on match conditions and so on. You do have to do a soft reset, so you have to clear the BGP process on the router if you do modify this attribute, because it does propagate, unlike the weight attribute, which is locally significant. So you can do a clear IP BGP soft in out, and remember that soft means that we're going to reset the routing information without tearing the session down. And in-out just means, am I going to reset it for my inbound session, or am I going to reset it for my outbound session? All right. Now, when I do use that BGP default local preference command, it's going to set the local preference on the updates that go out of the router to the peers within the same autonomous system. Remember, this is a intra-AS attribute. All right. So we receive the update from two different locations. Router C sets the local preference of all the updates to all of its updates from the peer to 150, and router D sets the preference to 200. And then we exchange that information all throughout AS51. All right. So both router C and D realize that the 10 network, 10.10.10/24 network, is reachable, but coming from AS20, we're going to have a higher local preference than the routes coming from AS10. So all the traffic from Area 51 is going to use router D as its exit point in this particular case. If we use route maps, that's going to provide us a lot more flexibility to be able to set these values. I'm not going to get into the actual configuration, but it's pretty much a match condition and a set condition. So I might say I'm going to go ahead and match, I'm going to create an AS path access list that says match AS30. It would look something like this. I told you I wouldn't get into the specifics, but it would look, I won't keep this in the notes, but I might do a match, IP, what is it, AS path access dash list 10, and then I would do a permit anything that starts with 20 and continues on with whatever. So I'm saying I'm going to go ahead and match all the prefixes that come from 20. Now, you could create a prefix list that matches a specific prefix if you only want to influence local preference for a specific prefix. But then you would do like a match ASPath 7 to match that ASPath access list and then set local preference to 200 or whatever value you want to set. Okay? Again, it's a 16-bit value, so we can manipulate that value as we see fit. All right. Next step, we're not going to go through all of these, by the way, because when we get to the tiebreakers, it gets a little bit complicated, but I do want to go through a lot of the primary attributes here, and then we'll wrap it up for today, and we'll start to get into some of the lab configurations on our next lesson. All right. Now, this particular attribute is really what we consider to be how the attribute was originated. Okay, so if we look at the type code origin, that's the attribute that we're talking about in this particular case. All right, so this is the this one's a little bit more difficult. I can't just say prefer the highest origin. Let's say I'm just going to prefer the path locally originated 0.0.0.0, okay, using a network command or aggregate command. So that'd be like a summary to originate a prefix locally on the router. All right. Aggregate is like a BGP subcommand that allows us to redistribute from an IGP into BGP. So these local paths are going to be sourced by either a network command under the BGP process or redistribute command, the confusing part of this, right, this particular attribute, is that there's a common misconception that redistribute is different than aggregate address, right? Redistribution is the process of taking routes from one routing process and inserting them into the BGP routing process, whereas aggregate address is a way for us to generate a summary into BGP of prefixes that already exist in BGP. All right, so local paths are going to be sourced by the network statement under the BGP process, or local paths sourced by redistribution into BGP, and that's just using a standard redistribution process, or local paths sourced by aggregate address. And actually it should have a dash in there, all right, which is essentially summarization. All right. And we'll get into that a little bit more later on. But there is even a selection process in this particular case. The network and redistribute, let me put this in, network and redistribute are preferred over aggregate address. All right. So we will look at this in the BGP table. We already did kind of look at this in one of our previous lessons. The origin code is listed. A question mark would be an example of an aggregate address or summary. There's other codes that allow us to identify how the route was originated into BGP. All right. All right. The next one is probably the easiest one to understand, which is number 4, and that is the AS path. And quite frankly, because we have we have essentially defaults for weight and local preference, we're talking about prefixes that we're learning from external peers. This is the first attribute that gets used the most in most cases. It is a well-known mandatory attribute, type code of number 2. All right, it's called the AS path. Very, very simple selection criteria. Prefer the shortest AS path. All right. Now, you can actually override this behavior if we say BGP best path, AS path ignore, as prefixes are propagated from one AS to the next, the AS path attribute collects the path information, and it adds it to this attribute. Can be ignored with the BGP best path AS path ignore command. Not generally recommended, but you may want to just simply ignore this attribute. Is going to be mean that we're going to ignore this particular attribute. In any event, the AS set, which is essentially a list of all the autonomous systems, counts as one AS path. All right. So there's not a whole lot to talk about with regards to. Let me put this counts as 1. All right, no matter how many ASs we go through. We did talk about confederations, confederation sequences, and confederation sets. Remember, those are not going to be included in the AS path link because they're local to that autonomous system that's running those confederations. But it's a really simple concept. For example, if I'm going back to this diagram here, the AS path to reach this prefix from this direction is going to be 5110. And the AS path to reach the 10.10.10.0 from this direction is 5120. Okay, well, and there may be another autonomous system up here that's being propagated as well. So we would have some value here and some value here. It's essentially built in the reverse order that it was created. Basically, this is for lack of a better term, hop count or hop by hop designation to identify how we reach a particular prefix. So it's a pretty simple selection criteria. We can do AS path prepending. We can manipulate the AS path attribute with route maps and AS path prepending. We can insert actual, what I would do, for example, in this particular case, one of the methods I could use to manipulate this is I could add my AS twice. Okay. What we do is we prepend the AS path attribute with our AS again, making this path longer, meaning that this path would be preferred in this particular case. Okay. All right. So let's go into one that is what we call an optional non-transitive attribute. All right. Which is, what number are we on? I think we're on step 5. Yeah. Step 5, which is to prefer the path with the lowest med. All right, what we call multi-exit discriminator. Or med value. Now, if I go back up here, med is an optional non-transitive attribute. All right. That means that my peer does either can choose to ignore the attribute, or even more than that, it may not even understand what the attribute is. But not only that, it doesn't propagate that attribute to the rest of the peers. Okay. So let's talk a little about this multi-exit discriminator. We need another topology diagram to basically describe how this works. Let's say we've got AS 65. Oops. AS 65. And we've got some routers in this topology. Okay. And we'll just call this router A, router B, router C. All right. And we have two ways of exiting this autonomous system number. And we'll just call this AS66. And there's a router in here that has a couple of prefixes behind it that we can reach. We'll just call this router ABCD. And we'll call this prefix X and prefix Y. Okay. So it doesn't really matter what the overall topology is, but what we need to understand is what the med is. So med is an optional non-transitive attribute, as I said. It's essentially a recommendation to my external peer about the preferred path coming into my autonomous system that has multiple entry points. Okay? And it doesn't, we can look at it from either perspective, right? So router B and router A could be advertising a med to router D or vice versa, but it is a suggestion. Let me make sure I put a note in here. A suggestion sent from an eBGP peer to another eBGP peer to suggest to that neighbor how they should enter my AS for a particular prefix. So this is the only time, outside of maybe manipulating AS path, this is the only time that I have an opportunity to influence a peer on how they leave their autonomous system and come into my autonomous system. In this particular case, lower is better, which is kind of strange because up to this point everything has been higher, and so on. So in this scenario, let's say that we've got AS, go back to my diagram here, try and think about how we want to manipulate this. So we've got AS65 and AS66. AS66 is a customer of the service provider in this particular case, which has the service provider. So let me just, this is my service provider and this is the customer. So, which has an AS of 65. Router D is connected to two different routers on the ISP side for redundancy, and it's going to advertise the two networks to the ISP, which is network X and network Y. All right. I didn't put prefixes here because it's too much to type, but we're advertising those two prefixes to the service provider. All right. And we have the two links for redundancy purposes and so on. All right. Now, as far as the peering relationships go, It's a pretty standard configuration, just eBGP peering relationships. We don't need to look at the specifics, but as far as like router B and router C, they're not really doing anything specific. They just got a neighbor specified on this link here. We got a neighbor specified on this link here for router D. We're not manipulating anything coming into Autonomous System 65. We're just accepting the attributes and the prefixes from router D. On router D, though, we have a little bit of a different scenario, right? And by the way, there's some iBGP peering relationships as well. So router B is an iBGP peer with router A, router C with router A, and so on. All right. The routers themselves, router B and C, they're going to pick the best path for those external routes based on the best path algorithm. All right. And we don't, in this case, everything is the same because we haven't manipulated anything. So based on the best path rules, eventually we're going to get to our tiebreakers and we're going to choose the path with the lowest router ID because everything else is equal. All right. So if router B has a lower router ID than router C, then we're going to simply choose that router to leave the network. Okay. Because remember, we're not using traditional metrics. We're not looking at the speed or the bandwidth of those particular links. We're just making decisions based on the best path selection process. So if I go back to router D now and I set the MED for prefixes, so I would do this based on a neighbor relationship. I'd have a neighbor statement for each of those peers, and I would apply a route map to those neighbors for outbound instead of inbound. And the route map would match these prefixes, X and Y. And then what I can do is I can set the metric by using the set metric command for those prefixes. So I could say, prefer this path for this prefix and prefer this path for this prefix. And I can do it obviously vice versa for the other peer. So I could say, okay, I want you for prefix X, I want you to go this way. For prefix Y, I want you to come this way. It's kind of a way that we can do some semblance of load balancing with failover without actually implementing load balancing. All right. And again, we're not going to get into the specific configurations because that's not necessarily what part of this discussion is all about. But remember, in the case of MED, lower is better. All right. So we can manipulate this value with route maps just like before. The peer or peers can choose to ignore the selection or the suggestion, I should say. Remember, it's an optional non-transitive attribute. So they can say, you know what? I know you're sending me a MED value. I'm not going to use MED as part of my selection criteria. So I'm going to ignore it. So even though you can maybe potentially influence how the router routes, it doesn't necessarily guarantee that they're going to route that way. Okay? So this is kind of a more complicated attribute. You do need to clear the sessions with the clear IP BGP star soft out to make sure that if you're modifying the MED values, that's going to take precedence or that's going to be done. But we'll get into that, like I said, in more detail. I think we'll probably see an example where we're manipulating these values. I doubt that this is one of those attributes that you're going to have to modify in the lab exam, but you never know. All right. So if I set conversely the MED to 100 versus 200, obviously in this case the 100 is going to be preferred. So I can say, you know what? Let's go ahead and set the MED. I should circle. There's my Y, and there's my X. So if I set this to 200 and 100 respectively, Oops, I did it the wrong way. Let me erase that and go backwards here. If I set this to 100 and 200 respectively, and then this is 100 and 200 here, lower numbers preferred, so we're going to end up routing over that particular link. Okay? Now, it gets a little bit more complicated because you can enable a command called the BGP deterministic med command. And that actually removes what we call temporal dependencies of the med-based best path decision, all right? Which means that we essentially do an accurate comparison across all routes that are received from the same autonomous system for those particular prefixes. I'll probably get into that a little bit later on. Like I said, this one is a bit more of a complicated attribute because there are several different ways that we can analyze this particular attribute. Okay? And I believe I skipped one. Now that I'm thinking about it, I'm going through my process in my head and I'm like, wait a minute, there's one that I missed. Doesn't change what we learned about this attribute though. Okay, yeah, this should be number 6. Can't believe I skipped one. Well, that's okay. We'll go to number 5 then. Okay, number 5 is origin type. In this case, we prefer what we call lowest origin type. This one's pretty easy, by the way. Lowest origin, not to be confused with locally originated. So originated and origin are completely different things in this particular case. And when we talk about origin type, we're basically talking about the administrative distance of how the route was learned. All right? So IGP protocols generally have a lower value origin than EGP, and EGP is lower than what we call incomplete. So we're not looking at administrative distance specifically because we know that eBGP has an administrative distance of 20 and iBGP has an administrative distance of 200. But if I'm learning about a path through an IGP process, if I learn about a path, a prefix, through an IGP process, I will prefer this over eBGP. Makes sense, right? Because if that path exists within my internal domain, that means it must basically originate within my autonomous system. It might be getting repropagated to me through an eBGP process, but I'm going to ignore that over the IGP process. All right? EGP, I should just really call this EGP because we're talking about IGP versus EGP. Still the same concept though, by the way, still eBGP. And EGP is preferred over what we call incomplete. All right, we'll learn more about how incomplete routes get generated and what constitutes an incomplete route. It basically is how that prefix is being learned in the BGP process. But we'll get into that a little bit later on. All right. Number 7. All right. Pretty simple one as well. I'm going to prefer eBGP paths over iBGP paths. Now this is a little bit counterintuitive, if you will, saying I'm going to prefer something external versus internal. But we're not learning about this prefix through an IGP routing process. This is somehow a route that's being sent into iBGP. But if I'm learning about the same prefix from an eBGP peer, that means that that prefix must exist outside of my autonomous system. All right? We're always going to prefer to route out of our domain for external prefixes than to try to route to a particular destination using an internal peer. All right. Now it gets a little bit more complicated when you deal with AS confederations and confed sequence. There's a distinction between confederation external and confederation internal, but we're not going to get into that right now. Now we're starting to get down to what we call the tiebreakers. There's really not a whole lot I can put for number 7 here. Not a lot to say about it. Here I'm going to prefer the path with the lowest IGP metric to the BGP next hop. All right. A lot of times this is also how we end up reaching a particular destination. All things considered equal, I'm just going to go ahead and use my metric to reach the next hop through my IGP routing process to be able to identify my exit point from the autonomous system. All right. All right. Number 9, I don't know if I really need to mention it, but that would be, are there multiple paths that require the installation in the routing table using BGP multipath? I'll just put, for now, because we'll talk about this later on, multiple paths. And by the way, we're usually never getting down to this selection process. Require, we'll just say, multiple routes with BGP multipath. I'll talk about BGP multipath a little bit later on. The concept of BGP multipath allows the installation into the IP routing table of multiple BGP paths for the same prefix. They're installed in the routing table together as the best path to do load sharing. All right. Now, the multipath option does not affect the best path selection. So the router is still going to designate one of those paths as the best path based on the algorithm, and it's going to advertise that best path to its peers. But in order to, for us to even consider a route as a candidate for multipath, they have to have the same characteristics of weight, local preference, AS path link, origin, MED, neighboring autonomous system or sub-autonomous system, AS path, and so on. And so there's a lot of criteria that would have to be met in order for us to be able to qualify a route down to this level. All right. There's 10, 11, 12, and 13. I don't know that I need to document those. If both paths are external, we prefer the path that was received first. So that's number 10. If both are external, prefer the oldest route received first from the peer. There's other criteria that we would have to look at. The router ID would have to take into account. There is no current best path. We'd have to take that into account, and so on. In the case of a tie here, now we're really getting into the tiebreakers. Now we prefer the path for the prefix from the BGP peer with the lowest router ID. Okay. The router ID is, as we talked about before, can be manually configured with the BGP router ID command, or it can be the highest active loopback or the highest active physical interface. Now, if I do have route reflectors, if I have route reflector attributes, the originator ID gets substituted for the router ID in that particular case. All right. Now, we're really getting into the weeds here. If the originator ID or router ID, let me say or, are the same, all right, we prefer, and this would be the example of, where you have multiple clusters and you've created this kind of redundancy group. We're going to prefer the path with the lowest cluster list length. All right. And then finally on number 13, we prefer the path from the neighbor I'm trying to think if it's the highest or lowest. I believe it's the lowest, with the lowest neighbor address. That's literally based on the physical address that we specify. That's the IP address that's actually used in the BGP neighbor configuration command. All right? And it's the address that corresponds to the address that we're using for our TCP connection with that local router. Whew. Lot of information here, right? Most of these attributes we don't even have an opportunity to manipulate, but certainly some of these earlier attributes we can utilize these attributes to make path selection processes. And that's what we're going to do over the next few lessons. That's why I wanted to kind of talk about this as part of the process. How do we customize that best path selection process? And you can do that by using the BGP best path command. So for example, you can skip any of these by saying BGP best path, whatever, cost community ignore, or whichever attribute you decide that you want to ignore as part of the process. For example, multi-exit discriminator, somebody might decide, well, I'm going to go ahead and ignore that value based on that, that multi-exit discriminator based on that ignore. Okay? So a lot of different choices. Okay? But I think we'll wrap it up right now because we're going to see all of this again later on. I'm going to go into more detail on this in one of our future lessons. But hopefully this gives you an idea of what we're talking about when we start to talk about these attributes in more detail. All right. You guys have any questions? All right. Well, we'll go ahead and wrap up this lesson.